This is Physics 2211, Lab 4, Oscillations. The purpose of this lab is to analyze the motion of a mass attached to a spring and compare that motion to a computational model to ensure the motion is accurate. Then using our model, we want to see if the energy principle is followed. To do that, we're going to use Newton's second law. So we'll have a force of gravity acting down on the mass and a force of the spring acting up on the mass. And we will also use it to find the new position and velocity, and we're going to do that using the update formulas, which we'll see later in the code. Then we're also going to use the energy principle, which says if that no work is done on the system, the change in energy will be 0. So delta E equals W. And a preview, since we're assuming no work is being done by the surroundings, we should see that the change in energy is 0. So here's our tracker data. So our system is the spring, mass, and the earth, and we have no surroundings. So when this mass is dropped, it's going to begin to oscillate back and forth. And we see our initial position right here, which we'll use in the model. The mass is 0.402 kilograms, and the initial length is 0.7 meters. And then there's no initial velocity, it is dropped from rest. All right, so here's our our calculated initial positions. So to get the spring constant, we're going to find the time of one period, which is about 1.619. And then using the formula, we can rearrange that to find the spring constant. And then for the resting length, we can use the formula, use the k that we got here, find that it's that. And then we will use that in the glow script model. Okay, so first of all, why are we using glow script? It's very tedious to go through and mark the center for each frame. There were over 100, so it takes a while. So it's much easier for a computer to do it for us. So here's the code. It has a few simple equations. Here I'm just saying that S is L minus L naught. Kinetic energy is 1/2 mv squared. Potential energy is mgh for gravity. And potential energy of a spring is 1/2 ks squared. And then over here, I changed the time to 9.5 because that was the last time in our model. Then to get net force, we have force of gravity, which is negative mg, and force of the spring, which is negative ks L hat. Just add those together. And then here's where we use Newton's second law. We have our velocity and position update formulas. And then this is just the same as before, just to update it. Okay, so this is what we observe. The blue is the model, the red is the actual. And they're pretty close, but there are some errors. And this is why. So the center could be wrong in each of the frames. Like I said, there's about 100 frames that we analyzed. So the odds that the center is accurate for each one of those is very slim. And in real life, there is likely work done by the surroundings, such as air resistance, but the model isn't picking that up. So that could result in slight differences that we're seeing. So a few questions to end. Was this energy principle satisfied? Yeah, it was. So we see that the total energy, which is this orange line here, it remains constant at 0, which is what we expect since there is no work being done by the surroundings. And then another question we want to ask ourselves is looking at the periods of the X and Y oscillations. So we see that 1 in the X is about 1.7 seconds, but 1 in the Y is about 1.6 seconds. So they're slightly off. So since that number is used to calculate the K constant, our K constant could be different depending on if we're using a period in the X or the Y.